Welcome back, everyone. In this video, we're going to finish looking at Chapter 4 of the ebook by focusing on ions. We're going to look at the trends in ion sizes, ion charge, as well as what it means to have an isoelectronic series, and then we'll review all of the periodic trends that we've seen already. So let's first talk about ions in terms of their charges. It turns out that we can predict for many of the elements what ion charge they will have, whether they gain or lose electrons, and what that charge will be. And we can do so based on their location of the periodic table. So this brings up what we call the octet rule. That is, that elements want to form an electron configuration to reach noble gas configuration. And noble gases, which are in our 8th main group, those have complete octets. In other words, when you look at their configuration, they all have NS2 and P2 or NP6 configurations. In other words, we have 8 complete electrons in their outer shell, hence octet. And this turns out to be the most stable types of configurations. Therefore, when other elements form ions, they do so such that for the most part they will achieve this type of configuration. So for example, all of the elements in group 1A, as they lose one electron, they obtain the configuration of the noble gas just prior to them on the periodic table. Halogens are in group 7A, and they are missing one electron. They have an NS2 NP5 configuration, so they need one electron in order to have the complete octet. Those in group 6A have an NS2 NP4 electron configuration and therefore need 2 electrons. Hence, they tend to have -2 charges. Group 5A, those are NS2 NP3 configurations, and those then need 3 electrons. Hence, they will tend to gain 3 electrons. And so what we see here then is that for the main group elements, groups, those that are 1 through 8A, we can readily predict what their charges will be. The transition metals tend to be exceptions to the octet rule, and those are for reasons that we won't talk about in Chem 110. You'll notice in some of the cases they tend to follow what we would expect, but in other cases they do not. And so you will be expected to be able to predict the common ions for the main groups, but not for the transition metals. As mentioned earlier, when we look at the electron configuration of ions, elements will gain or lose electrons in order to obtain that noble gas configuration. So this is just demonstrating again a scenario of what might happen. So sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1, and when it forms a cation, it loses the electron in the 3s orbital and donates it to chlorine, in this case, which then allows the chlorine atom to fill its the third shell and have a complete octet. So we see as ions, the elements tend to form, in both cases, the noble gas configurations. And as a rule, when you're removing electrons from an occupied orbital, remove from the highest n value, and then if you have two different n values, or 2 subshells you're considering of the same n value, you remove from the highest L value first. So for example, if we were to remove from chlorine, we have 2 different subshells with the same principal quantum number n, a value of 3. So you remove from the one with the highest L value first. We have the p orbitals and then the s orbitals, so we would remove first from the 3p subshell. So if we were to end up with chlorine plus, then that would have a core of neon followed by 3s2, 3p4. Transition metals are exceptions to the octet rule, as we mentioned. We've also talked before about the valence electrons being those in the outermost shell. For transition metals, this includes the elements in the n-1 d subshell, so long as that d orbital is not filled. So, for example, if we take a look at iron, iron's electron configuration would be a core of argon, then 4s2, 3d6. It then has 8 valence electrons. The 4s electrons, and then the 3d electrons. And so when we remove the electrons, we want to follow the same pattern that we talked about before. Remove the electrons from that are occupied in the highest n value before removing those with a lower n value. So if we remove electrons from iron, we're going to remove from the 4s subshell first. So iron 2 plus would have a configuration of argon with then 6 electrons in the 3d subshell. So this might be a little bit counterintuitive because we've talked before about how the 4s subshell is lower in energy than the 3d subshell. But it turns out that when we remove the electrons from our transition metals, we are still going to remove from the 4s subshell before the 3d subshell. Once those 3d subshell electrons go into the 3d subshell, they end up being lower in energy than the 4s subshell. And so hence we remove the 4s electrons before the 3d electrons. It's also important to note that transition metals can have variable charges. This is why, as we said earlier, we can't readily predict them. So you would need to be told some information about what their charge is. And again, as a reminder, when removing electrons to form an ion, you remove from the largest n value and then the largest L value within a given shell. Let's do some practice here. So, what would be the expected charge of a calcium atom when it forms an ion? Pause the video and try this on your own. Welcome back. So, we know that calcium is in group 2. So, in order to obtain a noble gas configuration, it's going to lose 2 electrons when forming an ion. Therefore, it has a charge of +2. It has lost 2 negative charges, and so it has a +2 charge. Second question. How many valence electrons does titanium, atomic number 22, have? Pause this and try this on your own. Welcome back. So, titanium's electron configuration would be argon 4s2 3d2. Remember that for transition metals, you include both the s and the d orbital electrons as part of the valence. So for titanium, it has 4 valence electrons. Third question. How many unpaired electrons are present in the ground state of the nickel 2 plus ion? Pause this and try this on your own. Welcome back. So, the first thing to do is to write out the electron configuration of the nickel metal, the neutral metal. Then you want to remove the 2 electrons. Remember, we remove from the highest n value first. Since the 4s is higher in n value than the 3d, we remove those electrons first. Then, if we draw out the orbital diagram and include the arrows, we would see that we have to have 5 half-filled subshells and then add 3 more electrons in, and so we have a total of 2 unpaired electrons. Let's now talk about ions and the sizes and their trends. So we need to remember first that when we go down a group, there is an increase in the principal quantum number n, therefore the size increases. We saw this already. So we see that the atoms get larger as well as the ions. Now, because we are losing electrons to form a cation, there is a larger attraction within the nucleus to the electrons that remain. For example, if we take a look at lithium, lithium has a total of 3 protons, and the neutral element has 3 electrons. So the ratio of protons to electrons is 3 to 3 or 1 to 1. When we remove an electron, then we have 3 protons and 2 electrons. So now there's a higher ratio of protons to electrons. Therefore, they pull the remaining electrons in closer to the nucleus. And so that's why we end up with a decrease in size when we form a cation. Anions have the opposite effect. You'll notice that if you take a look at the neutral atom compared to the cation, or excuse me, the anion, that anions are larger. And the reason for that is similar to what we saw for the cations. For an anion, let's take nitrogen. Nitrogen initially has 5 protons and 5 electrons. However, if we look at nitrogen 3-, it has 5 protons and 8 electrons. There are then fewer protons to pull those electrons in, and so as they repel each other, they spread out in order to minimize the repulsions. And that increases then the size of the anion relative to the parent neutral atom. We're now prepared to talk about what we call an isoelectronic series. The prefix iso means the same, and when we're talking about electronic, that's referring to the number of electrons. So an isoelectronic series is where we have elements that have the same numbers of electrons. So let's take a look first at a series of elements, nitrogen through aluminum on the periodic table. Notice that they all have the same initial core of helium, and then we have differing numbers of electrons in the subsequent subshells. If we take these neutral elements and we look at the most common ion forms of these, we would get nitrogen is missing 3 electrons, so it gains those 3 electrons to form a noble gas configuration. Oxygen gains 2, fluoride gains 1, neon is already a noble gas configuration, and then sodium, magnesium, and aluminum each lose electrons based on the excess number that they have here in the 3s subshell. When we form these ions, we now have added or removed those electrons, and we see that they all have the same noble gas configuration. So all of these form an isoelectronic series. So in order to identify an isoelectronic series, what you need to do is, if you're comparing ions to each other, you need to write out their noble gas configuration. Or rather, write out the electron configuration and determine whether or not they have the same noble gas configuration. If they do, then they are isoelectronic to each other. This is an image from the ebook that depicts isoelectronic series. The different colors indicate elements, or rather ions, that are part of the same series. And so you'll notice something, that the isoelectronic series will consist of anions with a lower overall number of shells relative to the cations. And again, that's because cations need to lose, or those elements need to lose the electrons as they become cations, to have the noble gas configuration. And so these noble gases here have the configuration that these other elements obtain when they gain or lose their electrons. Now, let's practice and take a look at some periodic trends. So which of these would be larger? Potassium, metal, neutral potassium, or potassium cation? The answer here is the potassium, the neutral atom of potassium. And that's because cations are smaller than their parent atoms. Looking at fluorine versus fluoride, which of those is larger? In this case, it's the fluoride anion. Anions are larger than their parent atoms. What about between sodium and magnesium? Sodium 1 plus, magnesium 2 plus. Well, in this case, because you're looking at elements of different charges, you probably want to think this might be an isoelectronic series. When you take a look at their electron configurations, indeed, you see that they both have a configuration of neon. Therefore, they are isoelectronic. And so when we look at isoelectronic ions, the one with the highest number of protons is going to be the smallest. Hopefully that makes sense. In both cases, they're going to have 8 electrons. However, magnesium has 12 protons, where sodium only has 11 protons. Because of the 12 protons of magnesium, it attracts those 8 electrons better, more strongly than in the case of the sodium ion. All right, now I want you to try this one on your own. Pause the video and try it, and come back and I'll walk you through it. Welcome back. So if we want to rank these in terms of increasing atomic radius, there's a couple things to look for. One thing to keep in mind is that if you have two elements that have the same charge, then they are probably in the same family. And if they're in the same family, we can rank them based upon which row they're in. So the larger the n value of the valence electrons, the larger the element. So calcium is higher up on the periodic table than strontium, so calcium is smaller. Selenium is higher up on the periodic table than tellurium, and that should have a negative charge on it. So the tellurium is larger and the selenium is smaller. What about these other elements? Well, when you see elements that have different charges, what's best to do is to evaluate and see, are these isoelectronic or not? When you write out the configurations of the 4 remaining ions, you see that they're all isoelectronic and they have the configuration of the noble gas krypton. Since they're isoelectronic, we can determine their relative sizes based on the nuclear charge, the atomic number. So let's look at the atomic number for the remaining 4 elements. Bromide has 35 protons, rubidium has 38 protons, selenium has 34, and strontium has 37. So these 4 are isoelectronic to each other, and because they have different numbers of protons, we can rank them in terms of their size. So we know that strontium has the largest number of, oh, I've put the wrong number here. Let's double check this. Strontium is 38. Hopefully you caught that. Rubidium is 37. Excuse my error there. Okay, so therefore we can rank them. High number of protons means smaller elements. Strontium has the highest number of protons, therefore it pulls in those electrons closer to the nucleus. Selenium has the fewest number of protons for the given number of electrons, therefore those electrons are not held as tightly and they repel each other more. So if we put the ranking within the families combined with the ranking within the isoelectronic series, we get the following. Okay, that is it. Thanks for watching and have a great day.